Hello everybody, myself Prashant Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. So far we have completed two modules. In our last class, we were discussing about single phase full wave converter, actually with center tap type with resistive load. Now today we'll discuss about single phase full wave converter with center tap type with inductive load, that is RL load. See, this is actually the waveform of full wave rectifier, control rectifier, center tap type with RL load. Actually, basically the circuit like same, only the resistive load will be replaced by the resistive inductive load. Actually, if we this circuit, actually basically this circuit inductive load, that is resistor and inductor will be in series with so this load will be replaced by RL load, or you can say an extra inductance will be added with this resistor, so to make it a inductive load. Now come to the discussions of this inductive load. Its waveforms as shown. As I told you, this is the voltage, current, and assuming highly inductive load, so that the load current is continuous, that is present at all times. So resistor 1 or SCR1 conducts for 180 degree from alpha to pi plus alpha, and the load voltage follows the input voltage, and at pi plus alpha SCR2 is fired, SCR1 will be turned off, and since the supply voltage immediately appears across it and applies a reverse bias, SCR2 now conducts for 180 degree to that is from pi plus alpha to 2 pi plus alpha, and supplies power to the load. And as a result, see, this is like this. This is source. This is continuous load current. This is output voltage like this. Okay, this is the output voltage waveform, and this is the source current for SCR1 conduction. This is SCR2. Again, this is for SCR1, like this. So average value of the say actually this load voltage is given by Vg equal to 1 by pi alpha to pi plus alpha Vm sin omega t d omega t. See this one. Okay, this is average 1 by pi, actually conduction from alpha to pi plus alpha. Okay, and that will comes to actually 2 Vm by pi cos alpha. And output voltage at its maximum, when it is maximum, when alpha equal to 0. So if you put alpha equal to 0, so cos 0 1, so it is maximum 2 Vm by pi. And when alpha is 90 degree, and it's a negative maximum when alpha is 180 degree. So maximum when alpha is 0, and 0 when alpha is 90, and negative maximum when alpha is 180 degree. So this normalized value of the output will be cos alpha. Okay, so this is the normalized value. So now output RMS should be the if you plot the control characteristic between normalized value Vn as a function of alpha, so that's going to be shown here. This is like this. At 0 it is maximum, and that is at 90 degree it will be 0. Okay, and at 180 degree it will be again a negative maximum. So this is like this. So actually this is rectifier operation and this is inverter operation. Like will be like this. This is the Vm versus alpha plot. So actually RMS output voltage will be output that is equal to the RMS value of the source voltage Vs. So average value of output current will be given by this. If we divide this actually VO, actual average value of the output voltage divided by R. So this is equal to Vm cos alpha by pi into R. And the load current has an EMF. The output average current is given by this is like this. So this is will be minus EV divided by R. Okay, so this average and RMS values of the thyristor current are given like this. This is the average current. If you integrate over alpha to pi plus alpha of this average output current with respect to omega t, so d omega t, so this will give you the average thyristor current. Okay, so that will be half of average output current. And RMS value, so will be 1 by root 2 times half of so 1 by root 2 times average value of the output current. So this RMS value of the supply current will be given like this. So this will be RMS value of the supply current and RMS value of the average value of the output current will be same in that case. So the average value of the supply current equals 0 because its positive part area equals its negative part. So but the average for the half cycle is equal to the average of the load current. Okay, this is the half cycle. So the output power is given by this is the V into output average output voltage into our average output current. So this will be I use RMS square into R. So if the load circuit has an EMF, the output average power is given by this is actually output average power. Output average power is equal to product of average output current into average output voltage. That is equal to like this. So plus it is E into IO0 average. So the input power factor is given by like this. So output by this source power, that is like this. So this will be average output power divided by this one. Okay, and also this is the input RMS. This is input power. So that's why actually input power factor. This is P by S, actual output by S. So this will give us the center tap single phase power full wave converter, single phase converter with RL load. So once again, if we repeat this one, this will be like this. Actually going to the waveform, we are finding that voltage current are taking into inductive load as a highly inductive, so that load current is continuous, that is present at all times. So SCR1 will be conducting for 180 degree from alpha to pi plus alpha, and load voltage follows the input voltage that is shown here. This is the source voltage and this is the load voltage. So this will follow the input voltage. Okay, and since actually at pi plus alpha, SCR2 is fired, so that is SCR2 is on, and SCR1 will be turned off. and due to the since a supply voltage immediately appears across state, it is so it is in the negative half of the supply voltage, so it will be off, and after a reverse bias. So actually, Asia 2 is now conduct for again for the 180 degree from pi plus alpha to 2 pi plus alpha, and supplies power to the load. So what we are finding? We are finding here that is for the positive half, Asia 1 is being conducted for 180 degree, and that is from alpha to pi plus alpha, and Asia 2, and after that 180 degree Asia 1 will be turned off due to the say supply voltage increased across it is negative, so that will be reverse biased, and at that time Asia 2 will be turned on, and it will be conducted for the next 180 degree from pi plus alpha to 2 pi plus alpha, and it will supply powers to the load. So this average value of the load voltage will be given by how much, from 1 to pi alpha to pi plus alpha Vm sin omega t d omega t, and that will be actually coming to Vm by pi cos alpha. So from this equation of the output voltage, we are finding that it is when alpha is equal to 0, output voltage is maximum, and when it is 0, when alpha is 90 degree, and it is the negative maximum when alpha equal to 180 degree. So the normalized output average output voltage will be this cos alpha. Okay, it is shown here. So actually the control characteristics, if we plot normalized value as a function of alpha, so it will be found that the RMS output voltage is given by output RMS value and the source RMS value. So this will be like this. So at 0 it is maximum, at 90 it is 0, and at 180 it is negative maximum. So actually this average value of the output current is given by this output average voltage divided by R. So this will be like this. If you put the average value of this one, so 2 Vm cos alpha by pi. So load, if the load circuit has an EMF, the output average current is given by like this. So this is the EMF. So this will be output average current. The average and the RMS values of the thyristor current will be like this. This is the average current. So it is half of the output average current, and RMS value will be 1 by root 2 times the output average current. So the RMS value of the supply current will be given from this equation. This will be RMS value of the supply or source current will be equal to average value of the output current, and then the average, but the average for the half cycle is equal to the average of the, so this average value of the supply current equals to 0 because this positive part area equal to the negative area, but the average for the half cycle is equal to the average of the load current. So that is given here, and the output power is given will be like this. This is the output product of the average output current and output voltage, and this will be RMS value of the output current square into R. This is the output power, and if the load circuit has an EMF, the output average power is given by like this. So this is so this will be like this. If there is an EMF, so this plus EIO average. So input power factor will be P by S, that is output power divided by the supply power by input power. So that is equal to, this is output power, and this is your product of the source voltage and source current will give you the actually this is the input power. So input power factor will be this output power by this input power. Okay, P by S output actually it is the active power, and this is the apparent power actually. So that's all about this discussion of center tap single phase full wave converter with RL load. Okay. Now we'll discuss this inductive load with freewheeling diode for center tap single phase full wave converter. So a freewheeling diode is connected across this inductive load right now. This was the first case discussions where this freewheeling diode were not present. Now this freewheeling diode is connected across this load. So basically this is a center tap. This is a thyristor 1 for the positive half of the supply voltage, and this is for the negative half of the supply voltage. This will conduct for 180 degree, and this will be for another 180 degree. This is for negative half. So and in our last discussion, the load was basically inductive load, so RL load. Now we connect a prevailing diode across this load. This is the circuit diagram. So as a result, this modifies the this inductive load modifies the voltage and the current waveform of this voltage and current waveform figures what we have got so far in RL resistive inductive load or RL load, or simply we can get heavy inductive load. Now this will be modified in presence of this freewheeling diode. So actually as the load voltage tends to go negative, the freewheeling diode becomes forward biased and thus starts conducting. Okay, so this will start conducting, and this load voltage is clamped to 0 volt. Nearly constant load current is maintained by freewheeling say diode through by actually maintaining this freewheeling current through the freewheeling diode, and the average load voltage and load current will be like this. So this is actually average of load voltage, its equation, and it is output will be like this. So if we calculate this 1 by twice pi, so to twice of integration pi to alpha, alpha to pi root 2b sin omega t d omega t. So it will ultimately come as Vm by pi 1 plus cos alpha, and average current will be this will divided by R. Okay, so the average output voltage divided by R. So this will be Vm by pi R 1 plus cos alpha, and this is the circuit center tap RL load and freewheeling diode. This is thyristor 1. This is output current. This is the output voltage, say across this load. Now see, this is your source or supply voltage. This is output voltage actually. This one. Actually, this one output voltage. So see the basic difference here. Actually, it was like this. Yeah. See, this portion is not present due to the presence of the freewheeling diode. So as a result, profile will be modified like this. Okay, and that is shown here. See the difference. That is shown. See? So actually, this portion, which was due to the presence of the freewheeling diode, this output voltage is clamped to 0. Okay, that's that I told you. This is the load voltage is clamped to 0 volts. So at nearly constant current is maintained as a result. See the output current. So this is nearly constant. So previously there was a variation. If you compare this with only the presence of actually your RL load, see the variation. This is the output current actually. Okay. See, Actually, due to this, this diff of the output current is due to the presence of this negative voltage in the output voltage. So that and that portion has been modified due to the presence of this freewheeling diode, and it makes it nearly constant. Okay, so see, this is the difference. Okay, and this is the thyristor current, thyristor 1, and this is for thyristor 2. This is conducting for first 180 degree, that's from alpha to pi plus alpha, and this is for negative part, that is for another 180 degree. Okay, so this is actually freewheeling diode current. Here, actually, this is the voltage and current waveforms of this circuit. Now, this average load voltage and load current we have been calculated here. This is the waveform. So, freewheeling diode carries the load current during the delay period. See, this is the delay period. This is the firing angle is alpha. So, this is the delay period. And during this time, this freewheeling diode is carrying the current. Okay, that means current will be flowing through like this to this load on this freewheeling diode. Clear? So basically, this load is inductive. So that due to the change in didt, so the energy will be when this negative part. So this diode will be forward biased, and it will conduct the current through this, and as a result the output voltage will be clamped at 0 voltage. Okay, see, this is the diode current. Clear? So freewheeling diode actually carries the load current during the delay period, that is alpha, when the SCRs are off. Therefore average and RMS values of the current to the freewheeling diodes are like this. This is the average current, average value of the current through the freewheeling diode. That will be actually this one. Okay, and this is the RMS current. Okay, so the average and RMS value of the current through the thyristor will be given like this. This will be 1 by twice pi integration over alpha to pi. So output average current d omega t. So this will be coming into this portion, and the RMS value, you know, this is the square, okay, of the output average value square into this mean divided over, like, this is root. So root mean square value. This will be coming like this. Okay. So RMS value of the supply current will be given by this expression here. So root over of 1 by twice pi, twice of integration over alpha to pi, average output voltage, output current square d omega t. So this will be coming like this. So Vm into 1 plus cos alpha divided by pi r in the root over of pi minus alpha by pi. So average value of the supply current equal to 0 for complete cycle. But for half cycle, if we like RL, so if we take so average value of the supply current will be like this: Vm cos alpha pi by r into pi minus alpha by pi. Okay, so that's actually clear our say idea about the RL load in presence with freewheeling diode across it. So the basic difference is clear from their waveforms. That is due to the presence of the freewheel or flywheel diode. The output voltage is clamped at 0 volt, and the output or load current is modified in such a way that a constant output current is being generated. So actually during the delay time, this free wheel diode will be conducting, and its waveform will be like this. This is the waveform of the current through the thyristor 1. This is through the thyristor 2, and this is output voltage. This will be like this, and see, this is modified in the presence of freewheeling diode than earlier one with RL load. So with this we can conclude about our discussion on center tap type single phase full wave converter. So we have started these discussions of single phase full wave converter center tap type with firstly with resistive load, then with resistive inductive load or inductive load, highly inductive load, and then in addition with this inductive load we have connected a free wheel diode across the load, and we have seen the clear modification of the say waveform profile, voltage and current waveforms of the output say load output voltage, current, and through thyristors 1, 2, etc., and how it modify our say during with modification of the initially it was a resistive load, then resistive inductive load, and then flywheel diode across this load, and we got the clear say modification of the from resistive load to resistive inductive load, then to resistive inductive load, and say free wheel diode across it. So actually see, this is the waveform, initially resistive load waveform, this is output waveform, okay, this is actually current, then we got this waveform with highly inductive load. See, this is output waveform. This is not continuous, but this is not constant. Magnitude is varying due to these portions. Okay, of the inductive load. This back EMF due to this back EMF presence. Now, not back EMF, that's actually an EMF actually, load EMF output. So, and after that we have discussed, say by connecting a free wheel or flywheel diode across this load, and we got the clear modification of the waveforms of the voltage and the currents in presence of this say free wheel diode. So how it had modified this output voltage waveform. So this negative portion has been being clamped to 0 due to the presence of this free wheel diode, and this free wheel diode conduct during the delay time. So this is the delay time from 0 to alpha, from pi to pi plus alpha, and so on. So in this way, actually, this we are finding a constant output current. A constant output current. There is no any variations. So it's almost constant. So with this, we can conclude our discussions on this single phase full wave center tap type converter with various loads, resistive, inductive or highly inductive load, and say modifications of the waveforms by connecting a free wheel diode across the load, and how it has been modified from waveform from resistive load to inductive hybrid, and then with presence of the free will diode. And that's all about our discussion today.